Good morning, everyone. Well, we are starting very late. So today we'll be looking into Ohm's law and the analysis of direct current circuits containing resistors. So just as usual, I know you are conversant with Ohm's law. So Ohm's law relates current flowing in a circuit to the voltage supply and the resistance for the circuit. So Ohm's law says that the amount of electric current that flows through a metal conductor in a circuit is directly proportional to the voltage impressed across it for any given set of physical conditions. So that grammar is saying that V voltage V is directly proportional to current flow I, and then bringing in constant of proportionality, which is the resistance. Or the resistance is fixed for a given set of physical conditions. So we have a diagram here, which shows the circuits containing a battery. The battery supplies voltage across the circuit. A is an ammeter, B is a voltmeter, but we are interested in the current that will flow through the resistor. Before now, we should have known that the ammeter is a device that measures current flow, and it's a device that has a very low resistance, while a voltmeter is a device that measures the voltage drop across circuit elements or the voltage supply across the voltage source, and it has a very high input resistance. So what happens is that the voltmeter connected in this circuit, since it has very high resistance, will take just tiny currents, negligible currents, out of the current supplied by the battery. So along the line, we'll see what that means. And we should also take note that when we are talking about Ohm's law, we are interested in metal conductors. We are interested in metal conductors. The fact that a material is a conductor does not imply that that material is a metal. So we have some other conductors that are not metals, and they do not obey Ohm's law. So Ohm's law gives a direct relationship between the voltage supply and the current flow in the circuit. Okay, so materials that obey, that conductors that obey Ohm's law are called materials that obey Ohm's law are called ohmic conductors. Their potential difference and current flow have a linear relationship. So materials that do not obey Ohm's law, or conductors that do not obey Ohm's law, are called non-ohmic conductors. And the relationship between the current flow and the voltage supply is not a linear relationship. If you look at Ohm's law here, you'll see a linear relationship between the voltage and the current. But from other materials, you'll see some other non-linear variables. It may contain logarithm and the like. So, and that's if you see an equation that contains log, sine, and the likes, they are referred to as nonlinear equations. So semiconductors also conduct electricity, and they don't obey Ohm's law, but they conduct. So if along the line, if you are in science, engineering, you may still come across talking about some materials like diodes, transistors that do not obey Ohm's law. So I will say current flow. What is current? Current is the rate at which charges flow through a particular channel. So when you imagine your charges to be tiny particles that they are, the rate at which they flow through your wires, you can describe that to be current. So when the electrons are flowing slowly, the rate at which they flow, if it is very low, then we can say that the current flow is low. But when the electrons are rushing through the wires or rushing through the circuit elements or rushing through the circuits, then easily you can say that the current is large. And we should always remember that electrons are negatively charged, but it is difficult for you to imagine something that is negative to be flowing through the circuits. So to make our lives in interpreting the circuit, to make it more easier, the direction of current flow is taken to be opposite that of electron flow. So it's like conventional currents. If we talk about the real name, to say conventional currents, the rate at which electrons flow through this circuit, and the direction, since it's current, since it's conventional convenience, it's convenient to think about it to flow from positive to negative. So current flows from the positive terminal of a battery to the negative. But we should always have it at the back of our minds that electrons are negatively charged and they are surely flowing out of the negative terminal and not out of the positive terminal. So resistance is the opposition to this current flow. So a circuit, just like we've seen in Ohm's law, there is a constant of proportionality R. The resistance R is like an opposition to the free flow of current. So an opposition to the free flow of current. So when the resistance is large, you will expect the current flow to be small. When the resistance is small, you would expect the current flow to be large. So resistance here is just like the same resistance we have in nature. If you are facing a huge resistance, you would have a lesser tendency to move forward. And you can imagine, okay, so like the voltage, like we know for the circuit, the potential difference between the ends of the circuit and the voltage, like we noticed in while discussing capacitors. When we have circuit elements in series, the voltage supply to the circuit divides itself across all these elements. So we'll be looking at some different circuits, different configurations along the line. So good conductors, like we have on the screen, they offer low resistance. Since they offer low resistance, they permit free flow of electricity. They permit free flow of electrons. They allow large current flow. And the opposite for conductors, they offer high resistance and they limit current flow. Insulators offer very high resistance while superconductors offer zero resistance to current flow. So we have different circuit elements: resistors, inductors, capacitors, diodes, transistors. These materials may also offer resistance to free flow of current. So along the line, we'll get to capacitors, reactants, and the likes, and you see capacitors also impeding the free flow of current. So I will say a circuit. A circuit is a combination of circuit elements capable of converting electrical energy to other forms of energy. Let's go back to this circuit diagram. We have a resistor there. The resistor there can be your bulb. It may be your fan. It may be your cooker. It may be your television. That is the load. So the resistance, so let's take, for instance, we have different bulbs. We have 60-watt bulb, 100-watt bulb. Let's imagine them connected separately. The 100-watt bulb is expected to be brighter, right? The 100-watt bulb, we have a 60-watt bulb connected to the mains of 220 volts, and the 100-watt bulb connected to identical or similar 220 volts. You would notice that the 100-watt bulb is brighter than the 60-watt bulb. Then my question will be, which of them has the lower resistance? Which of them, the 60-watt bulb or the 100-watt bulb, which of them offers a lower resistance? Okay, I've heard two different answers. I've heard true, I've heard false. The 60-watt bulb offers higher resistance. The 60-watt bulb offers higher resistance. That is why low current will flow through, while the 100-watt bulb offers lower resistance, allowing larger currents to flow through. So the 60-watt bulb has a higher resistance than the 100-watt bulb, but larger currents will flow through that 100-watt bulb than the 60-watt. And that is the why since a large current flows through the 100-watt bulb, then you'd expect it to be brighter. When larger current flows through your fan, you would expect the speed to increase. When larger current flows through your cooker, you would expect it to boil your water quickly. So when we talk about the circuits, it's not easy for you to represent your fan, your cookers in the circuits. Since they are resistors, a simple way to represent a resistor is shown on the screen. And the battery, to draw a battery, you must have seen this. You represent a battery, a cell, resistors, ammeter, voltmeter, and other circuit elements. But I'm limiting to this for now, because so like you saw in the last class, we showed capacitor. Capacitors, it looks like a cell, but the height of the two vertical lines there are equal. And for the fact that the vertical lines are equal, it passes a message. They are parallel plates, containing equal and opposite charges. Unlike a cell, you have high potential at the terminal and low potential at the other terminal, which allows currents to flow. So when we are talking about this same bulb, the one that has low resistance allows each current to flow. Fine, that's easy to imagine. But all things being equal, when the power supply fluctuates, when the power supply from PHCN, or is it now IBDC, when the voltage supply increases, you would expect that bulb to be brighter. When the voltage supply increases, it means that the current flow should also increase. So we may want to think about the voltage supply or the battery to be like a pump. But this time around, it's not pumping electrons or it's not pumping water. Oh, thank you. So I was thinking about the battery to be like a pump. And this time around, not your water pump, but a pump that pumps electrons, pumps charges around your electric circuit. And you can also imagine, forgetting about the pump, we can think about an overhead tank with water. Water will definitely flow from the top to the bottom. Similarly, current will flow from high potential to low potential. The higher this tank, the higher the pressure you should expect, or the more water you have in the tank, the more the pressure you should expect, or the height of the tank as well. The higher it is, the higher the pressure you should expect. Similarly, in voltage supply, the larger the voltage, the larger the force with which it will use to pump electricity around the circuit. So let's have an example. What is the current flowing through the lamp in the circuit? So now the lamp here, we've seen it to be a 3 ohm lamp. The voltage supply, the battery is 12 volts. What is the current flow? So a smart move is to say, to bring out the important information from that and say voltage is 12 volts, resistance is 3 ohms, and what is current? Sorry, what is current? Then we should always remember Ohm's law, which is V equal to IR. And since we know V is equal to IR, then we should know that I is equal to V over R. And we know V, we know R, that is 12 over 3 ampere. And that is 4 amperes. So, like we've known before, but I'll tell you again, voltage supply is measured in volts, resistance is measured in ohms, while current flow is measured in amperes. So those are the SI units. And we will say current is the rate of flow of charges. That is the QDT. So the number of charges that flows through a particular point per time is current. So if you like, you may not want to call it amperes and call it coulomb per second. for the SI unit example. So motion of charges results from potential difference in the field. So like I said, in the battery, the terminals give us potential difference. We have a positive terminal at the higher potential and a negative terminal at a lower potential that permits current to flow around the circuit. So for current to flow, there must be potential difference. For water to flow from one tank through your tap, there must be pressure, there must be like atmospheric pressure for it to flow freely. There should be a difference in height. For water to flow freely from your tank, there should be a difference in height for it to just flow freely. And you will not expect water to just flow from your well to your tank without you having a pump. So that's how the battery works, just like a pump. It pumps currents, pumps electricity around the circuit. And the current that flows through that circuit depends on the resistance of the circuit. Just like, let me go back to this diagram of we have an overhead tank. So you can imagine this to be a overhead tank containing water, and this is a pipe coming down, and this is your tap. If you open your tap a little, if you open it a bit, if you open it halfway, the water flow will have a certain rate. When you open it completely, the water flow will increase. What we have done there is that we have adjusted the resistance to water flow. If you open your tap completely, you have reduced the resistance to water flow. By opening it completely, reducing resistance to water flow, then large amount of water will flow per time. So you can think about electricity in different ways. You can think about resistance also to be like blockages. If you have this your tap and there are blockages in the pipe, those blockages will contribute to the resistance of free flow of water. If we think about this room, for instance, and all of a sudden, a lion appears here. If a lion should just appear now, I would expect both the big and the small to run out. And the rate at which you run out depends on many things. What is the size of the dots? Well, I know some will still go through this another place. So what is the size of the dots will be determining the rate at which you go out. These dots are posing resistance to your free runaway mode. So, and it also depends on the size of the lion. If it's a baby lion, you do not need to rush. So that's a baby lion can be likened to be like a small battery. So, but a big lion is like a big battery. Let me not call it a big battery. A battery with high that supplies high PMM, that has a high that supplies high potential difference. Such will cause you to run out through all the available spaces and even go to the wall. So we can have resistors connected in series and parallel, just like we did in capacitors. And there is still some basic rules that you must have at the back of your mind. Number one is that when resistors are connected in series, so let me not say resistors, when circuit elements are connected in series, the same current flows through them. the same current flows through them. The same electron that flows through R1 per time will flow through R2 per time, the same amount of electricity that flows through R1 without that will flow through R2 per time. So what that means is that I across R1 is the same I across R2, the same I across R3 and R4. And you can, and there is also another point we should note, which is that when we connect this particular across a potential difference across a voltage supply V, the voltage that will drop across R1 can be called V1. The voltage across R2 can be called V2. The voltage across R3 can be called V3, while the voltage across R4 can be called V4. So what this is telling us is that when circuit elements are in series, it is not compulsory that the voltage across each of them will be equal. They can be different. But what unites them is to say that the V that is across R1 to R4, that V is equal to V1 plus V2 plus V3 plus V4. So that's the what we should need. So when we imagine these resistors to be bulbs, electric bulbs, light bulbs, and they are glowing, if one should go off, all of them will go off. Because when one goes off, the current flow through it becomes zero. Since they are in series, the current flow through all of them will be zero. So when you imagine them to be any device, if they are fast, as long as for current to flow through all of them, they must complete the circuit. For current to flow through all of them, and we should note that the same current will flow through all of them. So when you have different bulbs connected in series, if their brightness is not equal, what that is telling you is that the resistance of those bulbs are not equal. If the brightness is not equal, that means the resistance of those bulbs are not equal. But since they are in series, the same current will flow through them. So if you take your 60-watt bulb again, and that's your 100-watt bulb, and you connect them in series, the 100-watt bulb, which has a low resistance, okay, let me see if I can draw something. You take your 60, I wish I can have a fresh page. Okay. Good. So let me just say we have a 60-watt bulb and 100 watts. Connected in series. So this has higher resistance. Let's just say okay. Let's say this as okay. Let me use the value. Let's just put high resistance, and this is low resistance. When they are connected in series, the same current will flow. The same current will flow. And when the same current flows through them, the potential across each of them would vary. So this is a V that we'll have here. The voltage across this will be that same current that is flowing times the I resistance. While the voltage across this will be the current, same current that flowed through that first one times the low resistance. So when the question is, what is the power? Okay, we'll get there later. Don't let me do it. Let me turn this on this. So when we are talking about resistors in series, we should not mistake them to be just resistors that are in a straight line. So when you look at this R1 to R4 here, they are in a straight line, they are in series. Similarly, at this corner, they are also in series. So you have to not just look at them that it's hovering, you have to look at it like the current that will flow through this resistor, is it going to be the exact road that will flow through the neighboring one? If yes, then they are in series. Okay, so before we get to resistors in parallel, so since we know that V1 is equal to V2 plus V3 plus V4, V1 plus V2 plus V3 plus V4, we call it V. And we know from Ohm's law that V is equal to IR. And we know that V1 should also be I times R1. V2 should be the same I times R2. V3 is the same I times R3. And V4 should be the same I times R4. If you collect the like terms, you say this is I into brackets R1 plus R2 plus R3 plus R4 equal to I big R. That R is now the total resistance because it's considering this point to this point to be V, while the points across each of the resistors to be V1, V2, V3, and V4. So simplify further, what do? You divide both sides by I. When you divide both sides by I, you'll be left with R1 plus R2 plus R3 plus R4 equal to R. And that is how to find an equivalent resistance for R1, R2, R3, and R4. So if you are designing the circuit and you want certain current to flow through a particular channel, and you resistor to stay at this particular point of the circuit, and you get to the market, you want to buy 200 ohm resistor and it's not available. All that is available is 100 ohms. Then you can buy two of such and connect them in series. When you buy two of such, connect them in series, you should have 200 ohms that will replace that single one you intended perfectly. So I will talk about resistors in parallel, looking at the R1, R2, R3, and R4 we have at the moment. What it tells us is that current is free to come in here, to come into this from the left. But when current comes in from the left, some will go through R1, some will go through R2, some through R3, some through R4, and they will all meet at this point and continue their journey. So R1, R2, R3, R4 may have different values. And when they do, you should not expect the same current to flow through them. So the current that will flow through this into this combination, if it is I, then we can, let me see, this is, then we can think of this to be I. So you can think of this to be I flowing in, and through R1, we have I1. Through R2, we have I2. Through R3, we have I3. And through R4, we have I4 flowing through. So what that simply tells us is that, so after flowing through each of these resistors, they come back to meet on the right-hand side with a value I. So in simple terms, it's easy for us to say that I is equal to I1 plus I2 plus I3 plus I4. Because the current that will flow through them is not necessarily meant to be the same. Just like we have them series, so combinations in series that the same current flows through, in parallel, the quantity that is common to them all is voltage V. So voltage V is common to them, the same potential difference drops across them. Also, when you connect your voltmeter across R1, you will definitely have the same value as when you connect it across R2 or across R3 and R4. So the same potential drops across them. Then it is easy for us to say that I, which is equal to, let me get a picture, to say I, which is equal to I1 plus I2 plus I3 plus I4. I is from Ohm's law. I is equal to what? V over R. I V over R. But for I1, it is V over R1. For I2, V over R2. For I3, V over R3. And for I4, V over R4. So when you collect like terms, you have V over R to be equal to V into brackets 1 over R1 plus 1 over R2, like that. So to simplify for that, you divide both sides by V. And when you divide both sides by V, you would have this long-standing expression that I know you must have committed to memory before attempting, like, so let's not bother. I hope there is no problem. I hope you can move. Good. So now we have an example that says R1, R2, R3 in the circuit below have values 2 ohms, 5 ohms, and 10 ohms. And a 6-volt battery of negligible internal resistance is connected across all the resistors. What amount of current will pass through the circuit? Okay, I think we can quickly have this done. Let me think about it. So easily we can say that let's quickly label this to say R1, R2, R3, 2 ohms, R2, 5 ohms, and R3, 10 ohms, connected across a 6-volt battery. So looking at this, easy approach is to think about the left-hand side, the combination on this left-hand side, thinking about them, fine, they are in parallel, these 3 are in parallel. So I will resolve them, replacing the 3 with a resistor that has the equivalent resistance of this force 3. Then that will now mean that I will now have a new circuit that will contain 4 resistors. That is the first resistor having a combination of R1, R2, and R3 in parallel. Now all being in series with R1, R2, and R3. So How do we go about this? For parallel, for the ones in parallel, these ones. It's easy for you to say that 1 over R total is equal to 1 over 2 plus 1 over 5 plus 1 over 10. So what do we do next? LCM. LCM of 2, 5, and 10. How do we do LCM? We draw a table, right? So 5 plus 2 plus 1. So 1 over R total is equal to 8 over 10, right? Then what is R total? R total is 10 over 8, which now becomes 5 over 4. 5 over 4 is one old number, 1 over 4, or 1.25, right? Okay, so good. So we can drop off the board again to say that we now have a new circuit. This time around, instead of having all these resistors, all these 3 resistors, we can replace these 3 resistors with a single resistor that is rated 1.25 ohms, right? So now think about it as now we are having a circuit with 4 resistors, 1.25 ohms, 2 ohms, 5 ohms, and 10 ohms. So what is the total resistance? It should be just simple addition. 1.25 plus 2 plus 5 plus 10, and that should be something like 18.25, right? Is it 17 or 18? Okay. So the total resistance, R total in the circuit is 18.25. While the voltage supply in the circuit is 6 volts, then the current flow should be what? The current flow I would now be what? V over R, and V is 6 and R is 18.5. So whatever it is, that is it. So I think we can brush over this one. I expect you to take this. Okay, before I forget, I've updated the LMS page with the previous slides up to last Monday, and I've also put the same information on my blog. I have a blog that is Physics 104.wordpress. Oh, come on, come on. WordPress.com. So the blog is for this class, and information pertaining to this. So if you have issues if you have full with LMS page, fine. If you have issues with LMS, this is also just to pass information. And some have been asking about recommended textbooks. It's on the blog, and I came with one of them, which is Fundamentals of Electricity and Magnetism. It was written by lecturers of the Department of Physics, and I've cited it severally. And I spoke with the publisher yesterday. He promised to make it available in the bookshop today from 12 o'clock. So when you get so I'm not one of the authors. Let me make a disclaimer. All the people that know this book are my seniors. So don't, so if you need it, so on the blog, there are some other textbooks that are there. So this is not the only book I consult, but I think it's worth recommending because it's our product. So let's, so also on the available recordings, I've also put on the YouTube channel, and the link to that is on the WordPress page. So you can always get the link from the WordPress page on to click on any video that's available. You know, there are some that are just expected to be available. Okay, so let's clear up the screen and see what we can do within 3 minutes. So looking at this circuit diagram, you would notice that looking at this circuit diagram, you notice that we have 9, 10, 11, 12 resistors and a cell. It is easy for you to think of R1 to be in series with R2 and also in series with R3, R4, and R5, and in series with R6, R7, R8, and R9, and also in series with R, A, R, B, and RC. So now we are going to try reducing the circuit one after the other. It's easy for you to take these three as that are in parallel, replace with a single resistor, take these four that are in parallel, replace with a single resistor. For these three, are they in series or in parallel? Series and parallel, or parallel and series? Okay. So a smart move on trying to resolve RA, RB, and RC is to start by taking RB and RC to be in series. And now saying both of them are now in parallel with RA. So I think the solutions are the solutions are there just to fill in the spaces. But unfortunately, if we begin to do that, we will run out of time. That is why every minute counts for this lecture, and not being able to start early is now a problem. So now we can replace R1 and R2 with a single resistor because these two are in series. So that is, and in this example, the solution are made to stand as the total resistance or the equivalent resistance of each of the resistors that we are adding up together will carry the name. For instance, R1 plus R2 is R12. So R12 is R1 plus R2. Since they're in series, it's easy for us to find an equivalent resistance to say that that is 2 plus 4 ohms. And RB, so this should be RBRC. Sorry, this is wrong. This should be RBC. And that should be RB plus RC. And that should be 1 plus 4, right? So 1 plus 3 ohms. So we should be ready to 6 ohm resistor. And this two with 4 ohms resistor. And that takes us to the next slide, where you can see we have a 6 ohm resistor now labeled as R1C, and a 4 ohm resistor labeled as RBC. Then resistors R3, 4, 5 would be treated as parallel, 6, 7, 8, 9, parallel, RA and RBC. Okay, that's parallel. So doing that would lead to finding equivalent resistance like you've done, which I recommend you do on your own. And if you do that correctly, you should have this circuit. This circuit, now we have been R1 and R2, R3, 4, 5, R6, 7, 8, 9, and RABC. And their values have been put in there: 6 ohms, 1.2 ohms, 0.8 ohms, and 2 ohms. So then the total resistance is now to see all the resistors in this circuit to be in series. And we now having the 10 ohm resistor. And then we will now see the current flow is V total, which is 12 volts, divided by the R total. Sorry, V rather, not V total. Divided by R total, which is 10 ohms. And that gives us 1.2 ampere. So the current that will flow through this circuit, that will flow out of this 12 volts battery, is 1.2 amperes. So what that tells us is that 1.2 amperes will flow through R1, 1.2 amperes will flow through R2, 1.2 amperes will split into 3 different fractions. Some will flow through R3, some will flow through R4, the rest will flow through R5, and they will meet here to be 1.2 amperes. They will get to this junction, split into 4, and meet here again to be 1.2 amperes, get to this junction, split into 2, one through the upper part, the other to the lower, and they will meet here to be 1.2 amperes and continue that journey. We should also note that the voltage across R1, R2, and these combinations will not be the same because the values of resistors are not the same. And when 1.2 gets to this junction and splits into 3, the larger chunk of that fraction will flow to the channel that has the lowest resistance, while the tiny piece will go through the one that has high resistance. Just like you share biscuits with your younger ones. So let's end here so that, because it's time already. So in the next class, we'll talk about simple circuit laws. Thank you.